Hi, I'm Ben-Yaakov. This presentation is entitled Parasitic Capacitance in Magnetic Devices and Tesla's patent US512340, or subtitled, Is it the first integrated magnetics? Now, wound magnetic elements like transformers or inductance do have capacitance in between the wires within the element, within the device. Shown here is a cross-section of a transformer. We have the primary, the black wires here, the cross-section are the primary, blue are the secondary, and then in between the turns of the primary and the turns of the secondary, we do have capacitance. Now, we can sort of represent this situation, although it's not accurate because this is a distributed system. We can do sort of first approximation, show it as a lumped capacitor here at the primary, lumped capacitor at the secondary, and now we can reflect the secondary to the primary, and we have a total capacitance. Reflection is times n squared, okay? Now, this total capacitance plus the inductance of the primary have a resonant frequency, shown here. This should be n squared. And therefore, you cannot use the transformer or inductor if you are approaching this frequency. So this is a limiting factor in the use of a magnetic device, wound, that you cannot approach this frequency. And if you need a device for high frequency, then you have to somehow find a way to lower these capacitances. Now, aside from the capacitance between the turns, we have capacitance between the layers, and therefore the total capacitance can be fairly high. And this is especially when shows up when you have a large turns ratio for high voltage, and in some applications you really have to worry about it because it gives rise to parasitic oscillation, like for example in a flyback. Now, if we look closer at what really happens here, is that I'm showing here two turns. There is a capacitance in between, and the two layers can be sort of represented by this transmission line. Again, it's a lumped presentation of a transmission line. We have inductance going all the way. It's one turn, the other turn, and then they are connected together. Now, there is a voltage drop across this layer, this turn. There is a current here, there's a voltage drop, and there is a voltage drop here. Now, since there is the same current flowing in these two, then as a first approximation, the drop is the same. So, if this is V1 prime is the end of, say, one turn, you connect it to the second turn, then this is the difference then between the two layers, and it's sort of kept throughout because, as I've said, as you go, the voltage drop is the same. So then you can say, therefore, that the voltage is this difference, and the energy now stored here, the energy stored here, is the total capacitance in between the two turns here. This is CT times the voltage of this difference here between the two turns squared over. So this will be the energy stored in between these two turns. So if I have a magnetic unit, and here's one leg which has n turns, and there is of course a capacitance between the turns, and say the total voltage across this section is V into 0, then of course the voltage difference between any two terms will be V over N, and the energy stored in one layer would be one layer would be CT VT over 2, and the N layer is times N. And then I can relate it to V in this way, which means that this is the total capacitance that will be seen here. So it's CT over N. This is not surprising considering the fact that we have here N capacitor in series, so the total capacitance is this capacitance over N. But this is for one layer. Now, if we are going to have another layer here, then of course there'll be a much larger capacitance. I'll talk about it later on. So now we come to the patent of Tesla. This was filed on July 7, 1893, and this patent is entitled Coil for Electromagnets. Let me first say something about the background. Tesla was concerned about electromagnetic devices and also wireless power transfer, and for that he actually needed a tuned circuit, that is a resonant circuit, because the impedance of the inductor is sort of not allowing the current to develop for a given voltage, and if you add a capacitor then you have a much higher current, of course the resonant current. So at that time capacitors were not that available, and in many labs they actually built their own capacitors. So this is the background, the need to get rid of this external unit, this capacitor. So here in the first part of the patent, Tesla is explaining the background. It says that in electric apparatus or systems in which alternating current are employed, the self-induction of the coil or conductors may, and in fact in many cases does, operate disadvantageously by giving rise to false current, which often reduce what is known as the commercial efficiency of the apparatus composing the system. And this means that the inductance or the reactance of the inductor is sort of limiting the current. And these effects of self-induction are known to be neutralized by capacity, that is capacitors, and these are condensers that constructed and applied in a separate instrument. That is, that inductors by themselves cannot provide the low impedance needed for the current, so therefore they need for capacitor to put in fact in parallel in this case with the inductors. So now the objective of this invention is, my present invention has as its object to avoid the employment of condensers, which are expensive, cumbersome, and difficult to maintain in perfect condition, and so to construct the coils themselves as to accomplish the same ultimate object. That is, to construct the coil such that it will have embedded in it, inherently in it, the capacitance. So you won't need a external capacitor, or smaller, you can get by with a smaller capacitance. And here is the idea. This is the so-called conventional coil at that time. This is a structure of, let's say, a pancake type coil. It's a spiral coil. You start here and you go all the way and then you come out. This is one layer, okay? This is used today, by the way, a lot in wireless power transfer for cell phones, etc. And here is the patent, or the invention. And the invention says that you don't wind it with one wire like this, but you take a bifilar winding. This is this winding, and well, it doesn't show here exactly. Actually, these two windings, that you start winding it. And then you go all the way around, and then you take the end of one of them and connect it to the other. And I'm showing you here in a simplified way. These are the two wires. You wind them together, and then you start here, the red one, at the end of the red one, you connect it to the black one, okay, here. So if you look at the current path, you go all the way here, all the way here, and then you go back to the beginning, in fact, to the black wire, and then all the way here, and then you come out. So this is the invention. And it's shown here for a number of 30 turns here, approximate. Now, What is the purpose of this whole idea and how does it work? Well, if we look at the original conventional winding, we see the following. We see that we start here, then we go all the way back, and then we come up here. Obviously, there's this different voltage, and then there's a voltage difference between V in and the voltage here of 1 turn. So this will be, if they would have been of the same diameter all the turns, this would have been, the difference here would have been V in over 30. But they are not. As you go down, the distance here is much, much shorter, and therefore the voltage difference between two adjacent turns is much smaller. So I have approximated by saying that the average voltage between the turn is approximately V in over 30. This is the number, and then I divided it by 2. So it's V in over 60. This would be the average voltage between turns. Now, in the case of the Tesla invention, we take the middle point and then wind it with the beginning. So therefore, the difference here is V in over 2. And then it goes this way all the way. That is, always there is a V in over 2 difference between the two, because as you go, there is a voltage here, there is a voltage here, and therefore, as you go around and around, you keep the same voltage difference between adjacent wires. Obviously, the voltage now is much higher than here, and therefore the energy stored, or the equivalent capacitance, will be higher. So let's have a look at it. Now, in the conventional one, I'm saying it's V in over 30, and then I'm dividing it again by 2. Actually, it could be more than that, but let's use this number. So it's V in over 60. So therefore, the energy is proportional to V in over 60 square. On the other hand, in the Tesla presentation, we have V in over 2, so it's V in over 2 square. So it's about, actually it's 900, it's about 1,000, the difference. It's a big, big, big difference. So you get much more capacitance, or an equivalent capacitor is much larger than in the conventional unit. Now, throughout the years, this idea of combining, say, capacitance and some other feature into one structure has been explored by many, many groups and many investigators in many labs around the world. One group, headed by Professor Daniel van Wyk, actually worked on this subject many years. And here's just one paper from 2001 in which they are showing how to combine the inductance, capacitance, and transformer into one unit. And here we have so this is a resonant converter. We have a resonant inductor. This is the magnetization inductance. This is now the transformer. Then we have capacitances here. This could be an LLC structure. Now, what they are showing in the paper, that they can combine all of these into one structure. Now, I'm not going into all the detail because this is above the scope of this presentation. I'll just talk a little bit about the capacitance part, these two capacitances. So what they're saying is the following. First of all, they're using a flat magnetics, which has the advantage of, first of all, for high current, but then also the area here is large, so that when you have one plate like this above the other, it's a turn here, one turn above another one, then there's a much larger capacitance in between, depending on the distance, of course, the dielectric material. And in this case, then you can actually construct like we have seen before. This is like the inductor, and these are the capacitance in between, so it's like a parallel resonant network. But if you go in one layer and then come out on the other layer, then this would be like a series resonance. So you can sort of put a series capacitor with this inductance. And they have actually built this structure which combines all these together. Now, what are the practical implications of all what we have said here? In a conventional way of winding a transformer, you start from here, you put on the turn, then you go back here, and then you go all the way back. Now, in this case, obviously the voltage difference between these layers here is only the voltage of one layer, but here we come to a point where the voltage is twice, because we have a drop of one layer, then a drop of another layer. So this will be the profile of the voltage across this section here. On the other hand, if you do the following, if after finishing one layer you go with the wire all the way here and start winding again, then the difference, or the voltage between the layer, will be always the voltage of one drop of one layer. Now, since energy is voltage square, then of course having a large difference here will bring about a more energy stored, or a larger equivalent capacitance. So let's have a look at it. If I just look at this profile, I come up with 1/4 of Vt squared for the energy, as compared to only Vt squared, which means that the equivalent capacitance here will be 30% larger than the capacitor here. It's not very large, but still it helps to reduce the capacitance. There are other ways to reduce the capacitance, and one of them would be to wind the wire in sections. That is, you start here, one section, then you go all the way here, another section, and then another section, and then another section. You know, in fact, you can put dividers here. So this will serve two purposes. First of all, the capacitance will be smaller, because you don't go all the way here, but the difference, the voltage drop is smaller here, so therefore the voltage difference is smaller here. And also, you get better insulation, because the voltage difference here is smaller than in a regular winding structure, and therefore it will maintain a higher insulation, so you can have a high voltage transformer on secondary here. Another way would be to wind it in a sort of a jigsaw way. Start with one turn, second turn, third turn, fourth turn, fifth turn, etc. By this, you minimize the voltage difference between the turns. You don't go all the way and then come back, but you have a smaller, of course, voltage drop in between these layers. Now, there is another implication here, and that is, if you need a high voltage output, obviously one way to go is to use a transformer 1 to n, and it will be a very large number, and obviously the capacitance that you reflect to the input will be very high. Another way to go is to break the secondary into sections. So this actually serves a number of purposes. Number one, of course, it reduces the voltage of each section, so therefore the rectifier is for lower voltage, the capacitor lower voltage. So this helps in this respect very much. But also it has an effect of the capacitance, because now we have the turn ratio is smaller. There is a point here that has to be considered, and that is, what is the capacitance of one section as compared to the capacitance of the total one. Of course, if it is one layer, the capacitance here will be lower than this capacitance. But if it is a multi-layer structure, then this capacitance here will be maybe approaching this one. So the question is, of course, how do you wind this, and how do you wind this? But I've just done here a very sort of approximate or first order calculation, assuming that the capacitance of this section is exactly as the capacitance of this total one. This would be for multi-layer structure, might be about the same. And therefore, while here we have n squared times Cn, here we have n over m. This is now the effective turns ratio between the primary and each of the section squared, but we have m sections, so it comes to be n squared over m. That is, we have divided this value by m, the number of sections, but as I've said, it really depends on how you wind it and what is the capacitance. If the capacitance of each section is smaller, which in many cases it is, especially for multi-layer structure, if this is smaller than this, then this number is actually smaller, so you get a total reflected capacitor which is much smaller. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting and perhaps it'll be useful to you in the future. Thank you very much.